What alarms scientists more than an asteroid on a collision course with our planet? It's the prospect of an interstellar body that could be observing us in return. The object known as Comet 3I Atlas is producing enigmatic emanations that imply an inner light source. This isn't merely the sun's light bouncing off its surface, but a phenomenon significantly more unsettling. Avi Loeb of Harvard labels it as a possible extraterrestrial probe masquerading as a comet, speeding through our solar system at 200,000 kilometers per hour while engaged in what could be a surveillance mission. The truly frightening prospect is not that an invasion is imminent, but that we are the subject of an evaluation akin to laboratory subjects under a cosmic microscope. Humankind is confronting its inaugural potential encounter with a superior intellect, and we lack any understanding of the standards by which we are being assessed. Join me as I delve into the most recent data and contemplate whether our species ought to get ready for enlightenment or annihilation. Part 1. Should we fear it? On the 1st of July 2025, a telescope situated in Chile's Atacama Desert detected a remarkable phenomenon, a dim blur of light traversing the starfield, bearing the undeniable hallmark of a voyager from beyond our star system. This was 3I Atlas, also catalogued as CI 2025-1, the third verified visitor from outside our solar system. Yet, in contrast to the two prior interstellar objects that visited our cosmic vicinity, 3I Atlas makes its appearance in an era where social media magnifies every rumor, where conjecture outpaces the speed of light, and where the boundary between scientific awe and existential apprehension has never been more delicate. NASA provides reassurance that no danger exists. The object is not projected to come any nearer than 1.8 astronomical units to Earth. That equates to approximately 270 million kilometers, a reassuring separation by astronomical measures. Its nearest pass to our Sun is anticipated for late October 2025, positioning it just within the orbit of Mars at a distance of about 1.36 to 1.4 astronomical units. Still, there is something about this visitor that feels distinct. Traveling at a speed exceeding 200,000 kilometers per hour relative to our Sun, both the Hubble Space Telescope and the European Space Agency have certified it as the most rapid solar system guest ever recorded on image. Its path is hyperbolic, not constrained by our Sun's gravitational pull, which mathematically confirms its extraterrestrial origins with certainty. Through our most potent telescopes, I observe a dusty coma enveloping what seems to be a nucleus with a diameter between 0.32 and 5.6 kilometers. The luminous haze I see is not the body itself, but a shroud of dust and gas surrounding a significantly smaller core. Recent spectroscopic examination by Spherex and the James Webb Space Telescope has identified carbon dioxide and water within this environment, signatures that suggest cometary processes rather than inert rock. But this is where the narrative grows more complex. Interstellar visitors are infrequent cosmic occurrences, and the two preceding ones, 1I Oumuamua in 2017 and 2I Borisov in 2019, triggered heated scientific discussions. Oumuamua's peculiar acceleration and the absence of visible outgassing prompted some scientists to suggest it might have an artificial origin. Borisov, thankfully, acted like a classic comet. Now, 3 Atlas enters our age of live social media commentary and 24-hour news cycles, where sensationalist headlines proliferate more quickly than peer-reviewed studies. The fundamental query that will steer my inquiry is deceptively straightforward yet profoundly significant. Is 3I Atlas a natural comet obeying the principles of physics? Or could some of its documented traits hint at something more extraordinary, possibly even technological? The implications of this question go far beyond academic interest. If I am mistaken about what is nearing our solar system, the consequences could fundamentally alter my comprehension of my place in the cosmos. I will scrutinize the discovery narrative in depth, examine the orbital oddities that have attracted attention, including its course near the ecliptic plane and its specific flyby meetings with Mars and Jupiter. I will look into natural causes for its conduct, weigh hypotheses regarding potential artificial origins, and scrutinize how institutions handle such exceptional claims. The current body of evidence firmly backs the finding that 3I Atlas is a natural carbon dioxide-rich comet traversing our solar system safely. Its makeup, conduct, and physical traits all correspond with what I would anticipate from a piece of ancient ice and rock that has roamed the galaxy for millions of years before happening upon our vicinity. But science requires more than just comfortable answers. I will meticulously probe alternative explanations, pit extraordinary hypotheses against the available data, and make a clear distinction between proven facts and speculative notions. When I come across claims that delve into the speculative, I will identify them as such, because the line between evidence-supported analysis and hopeful thinking is more critical than ever in our era of abundant information. As 3I Atlas proceeds on its path toward its October rendezvous with our Sun, it affords me an opportunity to study not only the object itself, but also my own reactions to the unknown. How do I strike a balance between sound scientific skepticism and an openness to new discoveries? How do I differentiate between sensible caution and debilitating fear? And perhaps most crucially, what does my response to this celestial visitor say about my readiness to face the possibility that I am not alone? The universe has delivered a messenger from the stars. Whether it brings stories of ancient comets or something far more exceptional, my reaction will be a test not just of my scientific tools, but of my wisdom as a species on the brink of cosmic consciousness. Part 2. Discovery of a Stranger. The tale of 3 Atlas commences not with a sudden flash of insight, but with the systematic patience that characterizes contemporary astronomy. The NASA-supported Asteroid Terrestrial Impact Last Alert System, or ATLAS for short, manages a network of telescopes tasked with scanning the night sky for objects that could pose a hazard. On that significant night in July, the station at Rio Hurtado, Chile, identified as W68 in astronomical records, documented what at first seemed to be merely another dim, moving point against the backdrop of stars. However, this specific blur of light held secrets that would soon transform my understanding of interstellar guests. The automated systems at Atlas diligently recorded the find and sent the coordinates to the Minor Planet Center, the international hub for such discoveries. What transpired next showcases the impressive effectiveness of our planetary defense systems. Within a matter of hours, observatories across the globe were pointing their instruments at this enigmatic newcomer. The validation that I was observing an interstellar trespasser arrived through orbital mechanics, the mathematical framework that dictates the movement of objects in space. When astronomers computed the trajectory of 3I Atlas, they uncovered something remarkable. Its orbit demonstrated extreme hyperbolicity, with an eccentricity markedly greater than 1. Put more simply, this object was traveling so swiftly that our Sun's gravity could never ensnare it. It was unmistakably just passing by. The statistical weight of this finding is immense. A study published in Astronomy and Astrophysics determined that the interstellar nature of 3I Atlas could be established with a significance greater than 700 sigma, a degree of certainty that renders the discovery practically irrefutable. For comparison, particle physicists typically announce a discovery at 5 sigma. 1700 sigma is a mathematical overabundance of the most gratifying kind. Yet the story does not conclude with that July finding. Astronomers quickly started sifting through archival records, a method known as recovery, to push the observational timeline further back. They found success in other 3 Atlas telescope logs and in the archives of the Zwicky Transient Facility, locating images of the object that went back to May 2025. This extra data significantly refined the orbital calculations, changing broad estimations into accurate forecasts. Why were scientists able to identify this as an interstellar guest so promptly? The key is the object's exceptionally high inbound speed and hyperbolic excess, technical phrases that detail how fast it was moving compared to what our solar system could naturally generate. Objects originating in our solar system are gravitationally tied to the Sun, tracing elliptical paths that bring them back repeatedly. 3I Atlas, in contrast, was clearly a single-occurrence visitor, possessing kinetic energy that suggested journeys across the interstellar expanse. Upon its initial detection, 3I Atlas was located at a distance of about 4.5 astronomical units from the Sun, approximately 675 million kilometers away, roughly the same distance as from the Sun to Jupiter. Its location against the star-dense galactic plane made initial follow-up observations difficult, but the worldwide astronomical community acted swiftly. The Minor Planet Center distributed circulars, NASA's Jet Propulsion Laboratory created ephemerides, which are tables forecasting the object's future locations, and planetary defense teams at NASA and the European Space Agency started to monitor its course with their usual precision. The object's name itself narrates a story of scientific revelation. At first given the provisional label A11PL3Z, it was soon upgraded to C2025N13I Atlas as its cometary character became clear. Ultimately, after its interstellar origins were confirmed, it was awarded the historic title 3I Atlas, only the third confirmed interstellar object in human history. This swift identification may appear to be standard procedure, but it is the product of decades of investment in planetary defense systems. The global network that monitored 3I Atlas comprises ground-based surveys, space-based telescopes, and advanced modeling systems capable of forecasting orbital changes with remarkable accuracy. Within days of its discovery, astronomers knew precisely where 3I Atlas would be for the duration of its journey through our solar system. However, it was this very orbital precision that started to spark speculation. The path of 3I Atlas, while definitively hyperbolic and unbound, showed one feature that seemed almost too neat. Its orbit was retrograde, moving in the opposite direction to the planets, yet it was tilted only about 5 degrees from the ecliptic plane. This indicated that it was moving in general alignment with the planetary orbits, a configuration that some observers considered suspiciously neat for an arbitrary interstellar voyager. The initial days after the discovery were characterized by widely fluctuating estimations of the object's size and brightness. This lack of certainty is entirely typical for newly found comets at great distances, where instrument limitations and atmospheric conditions can lead to contradictory measurements. But in our hyper-connected era, this scientific ambiguity provided fertile ground for conjecture. Each modification of the estimates, every new observation that refined earlier findings, was examined for some concealed meaning. What stayed consistent throughout this initial phase was the reassuring evaluation from NASA's Planetary Defense Coordination Office. 3I Atlas presented no danger to Earth. No preliminary tracking indicated any chance of an impact, and the object's path would take it safely by our planet at a significant distance. For the planetary defense community, 3I Atlas was just one more cosmic visitor to be documented and analyzed, albeit a notably fast and intriguing one. Still, even as astronomers endeavored to comprehend this new arrival, something about its actions continued to fascinate and at times disturb observers. The blend of its high speed, its near-ecliptic path, and the timing of its close passes by Mars and Jupiter seemed to imply a degree of cosmic coordination that challenged purely random explanations. As I will find, telling the difference between meaningful arrangements and cosmic flukes would become one of the main challenges in understanding what 3I Atlas truly is. Part 3. A Visitor Out of Place. Brightness Size Puzzles. When I, as an astronomer, try to ascertain the size of a remote object, I am essentially engaging in cosmic detective work with very few clues. For the majority of asteroids and comets, I deduce size by gauging reflected sunlight, making educated guesses about the surface's reflectivity, which scientists term albedo, and factoring in any surrounding clouds of dust or gas. With active comets such as 3I Atlas, this task becomes considerably more complex because the radiant coma frequently overwhelms the total brightness, effectively concealing the nucleus from my direct view. The observations of 3I Atlas by the Hubble Space Telescope gave me my first dependable limitations on the object's actual size. Following a meticulous analysis that considered the surrounding dust cloud, astronomers determined that the nucleus, the solid core at the comet's center, has a diameter between 0.32 and 5.6 kilometers. While these may appear to be broad limitations, they are at the forefront of what is achievable when examining such remote objects. Initial reports from a variety of observatories noted something particularly fascinating: an apparent forward-facing glow, or sunward plume, extending from the object. In the terminology of cometary science, this is sometimes referred to as an anti-tail, a phenomenon that happens when dust particles are propelled by solar radiation pressure and orbital mechanics, giving the impression of material moving towards the Sun instead of away from it. In the case of 3I Atlas, Hubble's high-resolution images showed a teardrop-shaped dust cocoon enveloping the hidden nucleus, a form that aligns perfectly with classic cometary behavior. However, it was spectroscopic observations that truly started to reveal the secrets of 3I Atlas. The SphereX mission identified an expansive carbon dioxide cloud stretching at least 348,000 kilometers across, a distance roughly equal to that between the Earth and the Moon. This vast carbon dioxide coma offered the first conclusive proof that 3I Atlas was actively outgassing, with frozen carbon dioxide sublimating directly from its surface into space as it was heated by the Sun's radiation. The James Webb Space Telescope contributed another vital piece to this puzzle. On August 6, 2025, JWST's near-infrared spectrograph captured spatially resolved spectra of the object, essentially generating a detailed chemical map of various areas within the coma. The initial findings displayed clear carbon dioxide signatures, corroborating SphereX's discovery with separate measurements. Nevertheless, as is the case with all pioneering science, these interpretations are still pending peer review and additional analysis. This leads me to what some observers have called the brightness anomaly associated with 3I Atlas. Several initial reports indicated that the object's brightness seemed unusually focused on the sunward side, sparking speculation about potential self-illumination or other unusual phenomena. However, seasoned comet experts quickly identified this as a probable instance of dust phase angle effects, a well-established optical occurrence that can cause cometary dust clouds to seem brighter when observed from specific angles in relation to the Sun. The emergence of sunward-pointing anti-tails is actually quite frequent in comets and is a result of the intricate interaction between solar radiation pressure, particle sizes, and the geometry of observation. Large dust particles, too massive to be easily swept away by the solar wind, can form extended structures that appear to point towards the Sun when viewed from certain vantage points. There is nothing enigmatic or artificial about this conduct. It is simply physics at work. A continual source of confusion in media reports has been the mixing up of coma size with nucleus size. Some early accounts claimed 3I Atlas was tens of kilometers in diameter, but these measurements almost certainly referred to the spread of the dust and gas cloud, not the solid nucleus itself. The Hubble constraints clarify that the actual object is quite small, a few kilometers at most, surrounded by a massive cloud of sublimating gases and dust. The discovery of both carbon dioxide and water vapor in the environment of 3I Atlas provides strong backing for the natural comet theory. Carbon dioxide sublimates at significantly colder temperatures than water ice, which clarifies why it is the dominant component of the coma at 3I Atlas's current distance from the Sun. As the object nears its perihelion in late October, I should anticipate seeing water vapor signatures become more noticeable as the surface temperatures increase enough to sublimate water ice. This volatile makeup narrates a compelling story about the probable origins and history of 3I Atlas. The existence of substantial carbon dioxide implies the object was formed in an extremely cold setting, precisely what I would expect for a body that has spent millions of years traversing the interstellar void. During this extensive journey, cosmic rays would have bombarded its surface, potentially modifying the chemical composition and creating the volatile-rich surface I observe now. Some researchers have tried to reconstruct the origin story of 3I Atlas by examining its trajectory and composition. Various teams have proposed that it might have come from the galaxy's thin disk or thick disk, regions with differing stellar populations and chemical makeups. However, these models are still highly speculative, and the true origin of 3I Atlas might forever be a mystery. The photometric behavior of 3I Atlas, meaning how its brightness alters over time and at various wavelengths, offers more proof of natural cometary activities. The observed brightness fluctuations are consistent with what I would expect from a rotating, sublimating nucleus encased in an active dust coma. There have been no sightings of unexplained brightness surges, structured thermal emissions, or other phenomena that might point to an artificial origin. As I continue to track the approach of 3I Atlas towards its perihelion, each new observation enhances my understanding of this extraordinary visitor. The combination of gas detections, dust morphology, and brightness behavior paints a coherent picture of an active comet carrying volatile ices that were altered during its long interstellar voyage. Yet questions persist. The precise composition of those ices, the internal structure of the nucleus, and the detailed processes propelling the observed outgassing all await further study. 3I Atlas may appear to be a simple comet, but its status as an interstellar guest makes every facet of its behavior scientifically invaluable. The main conclusion from current observations is evident. What I am witnessing seems to be the outcome of active comet physics, not technology. But as any good scientist understands, appearances can sometimes be misleading, and extraordinary claims demand extraordinary proof to either confirm or deny them. Part 4. The Alien Technology Hypothesis. In the field of scientific investigation, there are few researchers as prepared to explore contentious areas as Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and the founding director of the Black Hole Initiative. Regarding 3I Atlas, Loeb and his colleagues have put forward a challenging idea that warrants serious consideration, even if it goes against traditional astronomical views. Could this interstellar guest be artificial instead of natural? Loeb's case is built on several observational characteristics that he sees as potentially consistent with technology. The apparent sun-facing radiance noted in early reports, the object's path that takes it remarkably near the ecliptic plane, and its precisely coordinated flyby encounters with Mars and Jupiter all constitute, in his opinion, patterns that call for investigation beyond purely natural causes. Perhaps most fascinatingly, Loeb has suggested what he terms a reverse Oberth maneuver scenario. In standard space travel, the Oberth effect enables spacecraft to achieve maximum velocity by igniting engines when their orbital speed is at its peak, usually at perihelion, the point of closest approach to the Sun. A sufficiently advanced civilization, Loeb posits, might use the opposite tactic, employing the perihelion pass to brake and slow down by applying thrust exactly when orbital dynamics would make such actions most effective. This idea ventures into even more speculative realms with Loeb's discussion of possible mothership and mini-probe arrangements. The concept implies that what I perceive as 3I Atlas might be either a reconnaissance probe sent by a larger craft or perhaps a piece of an interstellar vessel that has fragmented during its extensive journey between the stars. Although these ideas are purely theoretical for now, they exemplify the kind of thinking necessary to consider all possibilities when confronted with unusual phenomena. Loeb has also publicly supported using current spacecraft to get closer looks at 3I Atlas during its Mars encounter in October 2025 or its Jupiter flyby in March 2026. The Juno spacecraft, which is currently orbiting Jupiter, could theoretically be moved to capture images with higher resolution as 3I Atlas passes by. Likewise, various Mars orbiters could potentially be reassigned for a more detailed study. However, the practicality of such observations is still in question given the intricate orbital mechanics and mission limitations involved. The most provocative part of Loeb's hypothesis relates to the potential for self-illumination. He has proposed that the apparent brightness irregularities seen in 3I Atlas might suggest some kind of artificial lighting or even nuclear-powered propulsion systems. This would be a significant deviation from natural cometary behavior, where variations in brightness usually come from reflected sunlight and thermal emission from heated dust and gas. To grasp these concepts correctly, I must view them within the context of Loeb's earlier work on interstellar objects. After the discovery of Oumuamua in 2017, Loeb co-authored papers suggesting that the object's strange acceleration and lack of visible outgassing could be explained by a light sail, essentially a thin, man-made membrane designed to be propelled by stellar radiation. While most scientists have since determined that natural outgassing of hydrogen gas can account for Oumuamua's behavior, the light sail hypothesis initiated crucial conversations about how I might identify artificial objects in space. The scientific community's reaction to these technological theories has been varied, but largely doubtful. The majority of astronomical observations of 3I Atlas align with conventional cometary explanations. The detection of carbon dioxide and water vapor, the existence of a significant dust coma, and the morphological traits observed by Hubble all correspond naturally with the expectations for an active comet. This leads me to a core principle of scientific inquiry. Extraordinary claims demand extraordinary evidence. While technological reasons for the behavior of 3I Atlas are theoretically plausible, no observations to date have found the types of signatures I might expect from artificial objects, such as structured radio signals, engineered materials in spectroscopic analysis, geometric features in high-resolution images, or signs of controlled propulsion or navigation. Yet Loeb's readiness to put forth these ideas plays a crucial role in the scientific method. Hypotheses, even speculative ones, help direct observations by suggesting what kinds of evidence I should be searching for if 3I Atlas were indeed artificial. What particular signatures should I anticipate? How would its thermal emissions be different from natural outgassing? What kinds of spectral features might indicate manufactured materials or controlled energy sources? The consideration of these possibilities also compels me to address a more profound question about my assumptions as I search for life and intelligence beyond Earth. How would I recognize genuinely alien technology? Would it necessarily align with my expectations based on human engineering principles? Or might advanced civilizations create technologies so advanced that they are almost impossible to distinguish from natural occurrences? For the time being, the weight of evidence strongly supports natural explanations for the behavior of 3I Atlas. The carbon dioxide detections from SphereX and JWST, the dust morphology shown by Hubble, and the overall behavioral patterns all fit with established cometary physics. No current observations necessitate the invocation of artificial origins to explain what I see. However, science advances by testing alternative hypotheses, and Loeb's technological scenarios offer valuable frameworks for assessing future observations. As 3I Atlas nears its close encounters with Mars and Jupiter, I will have chances to conduct more detailed observations that could either support or definitively dismiss artificial explanations. The essential thing is to maintain proper scientific skepticism while staying open to unforeseen discoveries. I should neither reject unconventional ideas without proper investigation nor accept them without compelling proof. In the instance of 3I Atlas, this means continuing to monitor the object attentively, looking for any anomalous signs that might support technological hypotheses while staying firmly rooted in the substantial evidence for natural cometary activity. Whether 3I Atlas turns out to be an exotic comet or something far more extraordinary, my investigation of both possibilities demonstrates science at its finest: rigorous, open-minded, and dedicated to following the evidence wherever it may lead. Part 5. The Case for a Natural Comet. The scientific method is built on constructing arguments from multiple, separate lines of evidence. When it comes to deciphering the true nature of 3I Atlas, the natural comet hypothesis is strongly supported by observations made across the entire electromagnetic spectrum. Each individual piece of evidence I examine points to conventional physics. When considered together, they form a persuasive case for 3I Atlas being a remarkable, yet ultimately natural, visitor from interstellar space. The most direct proof comes from the detection of gases in the immediate vicinity of 3I Atlas. Spherex's discovery of a vast carbon dioxide coma extending at least 348,000 kilometers provides undeniable evidence of active sublimation. This is the direct transformation of solid carbon dioxide ice into gas as solar radiation heats the object's surface. This process is a cornerstone of cometary physics and does not require any unusual explanations. The James Webb Space Telescope's identification of carbon dioxide features through spatially resolved spectroscopy adds critical confirmation to these results. JWST's unparalleled infrared sensitivity enables it to pinpoint molecular signatures with extraordinary accuracy, and the initial findings show precisely what I would expect from a carbon dioxide-rich comet at the current distance of 3I Atlas from the Sun. Equally significant is the morphological evidence from observations by the Hubble Space Telescope. The high-resolution images show a classic teardrop-shaped dust cocoon enveloping an unseen nucleus, a structure that aligns with theoretical models of cometary activity with remarkable accuracy. There are no geometric oddities, no engineered features, and no structural components that would suggest artificial construction. Instead, I observe the elegant simplicity of physics in action, a small, cold object warming up in stellar radiation and expelling stored volatiles into space. The size limits determined from Hubble observations, a nucleus diameter between 0.32 and 5.6 kilometers, are perfectly in line with expectations for interstellar comets. Objects of this size possess enough mass to hold on to volatile ices during long journeys through interstellar space, yet they are small enough for solar heating to trigger significant outgassing when they enter a stellar system. The extreme velocity and hyperbolic trajectory of 3I Atlas, while unusual by the standards of our solar system, are completely logical for an object that has traversed interstellar space for millions of years. Computer simulations of galactic dynamics indicate that objects ejected from other stellar systems will gather random velocities through gravitational interactions with stars, molecular clouds, and other galactic structures. An object with the speed and trajectory of 3I Atlas fits seamlessly into this population of interstellar travelers. Perhaps most importantly, I can directly compare 3I Atlas to 2I Borisov, the previous interstellar comet found in 2019. Borisov displayed classic cometary behavior, showing clear shifts from carbon monoxide and carbon dioxide dominance at great distances to water vapor dominance as it neared perihelion. The compositional parallels between 3I Atlas and Borisov suggest I am dealing with the same category of objects, fragments of primordial ice and rock that formed around other stars billions of years ago. The international monitoring campaign studying 3I Atlas is a testament to the success of collaborative science. Hubble provides size limitations and morphological analysis. JWST offers detailed spectroscopic identification of molecular species. Spherex maps the extensive coma structure. Ground-based telescopes like the Gran Telescopio Canarias contribute with photometric and compositional analysis while continuously refining orbital forecasts. Each instrument addresses different questions, and their collective findings create a consistent narrative of active cometary processes. A recurring source of confusion in media reports has been the misreading of size estimations. Some accounts have described 3I Atlas as being dozens of kilometers in diameter, but these measurements almost certainly pertain to the extent of the dust and gas coma, not the solid nucleus. The Hubble Space Telescope's thorough analysis, which takes into account the coma's contribution to the total brightness, provides much more precise limits on the actual size of the object. The question of the ultimate origin of 3I Atlas remains scientifically captivating but unresolved. Different research groups have suggested origins in either the galaxy's thin disk or thick disk, regions defined by different stellar populations, ages, and chemical compositions. Some models propose that 3I Atlas could be older than our solar system itself, a remnant from the galaxy's initial periods of star formation. However, these origin models are fraught with significant uncertainties, and the true birthplace of 3I Atlas may never be conclusively identified. The close passes by Mars and Jupiter that have drawn attention in some quarters are actually less extraordinary than they might first seem. Statistical analysis of hyperbolic orbits reveals that many random interstellar trajectories will naturally have close encounters with major planets just by chance. The fact that 3I Atlas will pass within 0.19 to 0.20 astronomical units of Mars and 0.36 astronomical units of Jupiter is more indicative of the size and gravitational pull of these planets than of any deliberate aim. Current monitoring efforts continue to bolster the natural comet theory. Photometric observations show brightness fluctuations that are consistent with a rotating, sublimating nucleus. Spectroscopic monitoring detects precisely the molecular species I would expect from warming cometary ices. Morphological studies show dust structures that align with computational models of cometary activity. No observations necessitate the use of exotic physics or suggest artificial origins. As 3I Atlas approaches its late October perihelion, I can make specific forecasts based on the natural comet hypothesis. Water vapor signatures should become more prominent as surface temperatures climb above the sublimation point for water ice. The rate of dust production should rise, potentially making the coma more easily seen by ground-based observers. The nucleus might start to show signs of breaking apart if thermal stresses overwhelm its structural integrity. These predictions are specific and testable, offering clear methods to either confirm or refute the natural comet interpretation. If 3I Atlas were artificial, I might expect quite different behavior. Stable brightness, independent of its distance from the Sun, the absence of volatile signatures, or geometric features visible in high-resolution images. For now, the scientific consensus strongly favors treating 3I Atlas as a natural though remarkable example of an interstellar comet. Its carbon dioxide-rich composition offers insights into the conditions around other stellar systems billions of years ago. Its successful retention of volatile ices during interstellar travel sheds light on the physics of small body evolution in the galactic environment. Whether 3I Atlas ultimately turns out to be an exotic natural object or reveals unexpected anomalies, my careful study of this visitor exemplifies science at its most fundamental level: the patient gathering of evidence, the testing of competing hypotheses, and the readiness to be surprised by what the universe unveils. Part 6. The Fear Instinct. To comprehend why 3I Atlas has sparked such profound interest and, at times, anxiety, I must delve into the unique psychology that shapes human reactions to cosmic occurrences. My brain, having evolved over millions of years to handle terrestrial threats, exhibits systematic biases when faced with the boundless scales and alien physics of space. These biases influence not just my personal reactions, but also the collective discussions that arise around mysterious celestial visitors. Psychologists have pinpointed a phenomenon they call dread risk, my inclination to overestimate the likelihood and severity of catastrophic yet improbable events. This mental shortcut was beneficial for my ancestors in assessing dangers from predators or natural calamities, but it leads to systematic distortions when applied to astronomical phenomena. A comet that poses absolutely no real danger can still provoke intense anxiety simply because it is an unknown entity from an immeasurably vast universe. The affect heuristic exacerbates this issue by directly connecting my emotional responses to my risk evaluations. Events that feel alarming are automatically deemed more hazardous, irrespective of objective proof. When I am confronted with something as foreign as an interstellar visitor moving at 200,000 kilometers per hour, my emotional systems are triggered long before rational thought can offer any comfort. Ambiguity acts as another potent amplifier of fear. In the initial weeks after the discovery of 3I Atlas, when orbital details were still uncertain and spectroscopic analysis was incomplete, the lack of definitive information created a void that speculation eagerly filled. Humans evolved in settings where unknown dangers could be fatal, so my inherent reaction to ambiguity is heightened alertness rather than patient inquiry. Modern media environments can escalate these individual psychological inclinations into widespread phenomena. The 24-hour news cycle requires a constant stream of content, and the uncertainty surrounding cosmic visitors is a rich source for sensational stories. Headlines that highlight mystery, speed, and unknown origins are far more effective at grabbing attention than balanced discussions of orbital mechanics and spectroscopic analysis. I can see this pattern distinctly by comparing media reports on 3I Atlas with official statements from NASA and the European Space Agency, where headlines use terms like mystery object, blazing speed, and unknown visitor. Scientific bodies concentrate on specific figures, distances, velocities, chemical compositions, and trajectory forecasts. The same factual data can elicit entirely different emotional reactions depending on its presentation. The case of 1I Oumuamua shows how these dynamics can unfold over time. Initial observations pointed to an object with unusual characteristics, an elongated form, no visible coma, and a slight acceleration that could not be explained by gravity alone. Lacking immediate explanations, speculation thrived, including theories about artificial origins. It was only after months of meticulous analysis that the scientific community reached a consensus on natural explanations involving hydrogen outgassing from processed water ice. Understanding these psychological patterns clarifies why planetary defense communications stress concrete, measurable facts over interpretative speculation. When NASA states that 3I Atlas will pass no closer than 1.8 astronomical units from Earth, this specific measurement serves several purposes. It delivers precise information for scientific analysis, provides tangible reassurance about safety, and showcases the accuracy and dependability of my tracking systems. Interviews with psychologists who specialize in the perception of existential threats offer fascinating insights into why cosmic visitors evoke such deep-seated responses. These objects trigger what researchers term archetypal fears, profound, culturally ingrained anxieties about invasion, judgment, and cosmic insignificance that are present in all human societies. The mere thought that I might not be alone in the universe challenges fundamental beliefs about my place in creation. Yet to focus solely on fear would be to miss a crucial opposing element, the capacity for wonder that cosmic discoveries can awaken. The same psychological mechanisms that generate anxiety about unknown threats can also inspire awe at the magnificent scales and elegant physics demonstrated by interstellar visitors. 3I Atlas presents an opportunity to observe material from another stellar system, to study chemistry that originated billions of years ago around distant suns, and to get a glimpse of the cosmic processes that form my galaxy. This ability to feel wonder has important functions beyond simple emotional gratification. Scientific literacy and public backing for space exploration are strongly linked to feelings of cosmic curiosity rather than cosmic dread. When people see astronomical discoveries as chances for learning instead of sources of danger, they are more inclined to support the research programs that broaden my understanding of the universe. The global cooperation needed to study objects like 3I Atlas is a prime example of humanity at its collective finest. Within hours of its discovery, observatories on multiple continents were exchanging data, coordinating observations, and constructing comprehensive models of the object's trajectory and composition. This reaction highlights not only my technical skills, but also my species' remarkable ability to cooperate when faced with cosmic mysteries. I can use these insights to create better methods for communicating about future astronomical discoveries. Media literacy is essential. Learning to tell the difference between peer-reviewed scientific analysis and preliminary conjecture, understanding the distinction between uncertainty and danger, and recognizing how framing influences my emotional responses to information. The risk assessment for 3I Atlas perfectly illustrates these principles. When I compare the actual risk posed by this interstellar visitor, which is essentially zero, with known impact threats from objects within our solar system, I see that my attention and worry are drastically out of step with the actual probabilities. NASA's Planetary Defense Coordination Office monitors thousands of near-Earth objects that present far greater statistical risks than any interstellar visitor. Yet these more commonplace solar system inhabitants attract much less public attention. Perhaps most importantly, I can acknowledge that my initial emotional reactions to cosmic discoveries do not have to dictate my final conclusions. Fear constricts my viewpoint, urging me to concentrate on threats and worst-case scenarios. Wonder broadens my perspective, inviting me to explore possibilities and to value the magnificent complexity of the universe I live in. 3I Atlas elicits both responses, but ultimately rewards the latter. Whether it is found to be an exotic natural comet or reveals unexpected characteristics, this visitor gives humanity a chance to show scientific maturity, the capacity to confront the unknown with curiosity instead of dread, to pursue understanding rather than to fall back on comfortable assumptions. As I continue to monitor the journey of 3I Atlas through my solar system, I am not merely studying an astronomical object. I am conducting an experiment on how my species reacts to contact with the truly alien. The outcome of that experiment will influence not just my understanding of this specific visitor, but also my readiness for the cosmic discoveries that lie ahead in the coming decades. Part 7. Ancient Omens, Modern Parallels. Long before telescopes unveiled the true nature of comets, human civilizations observed the heavens with a blend of reverence and dread. These unexpected guests, materializing suddenly against the familiar tapestry of stars, contested ancient beliefs about celestial harmony and divine purposes. The Chinese referred to them as broom stars, thinking they swept away ruling dynasties and foretold political turmoil. Imperial astronomers diligently documented their appearances, compiling records that modern scientists now employ to reconstruct historical orbital paths with remarkable accuracy. The most renowned instance of cometary fear ingrained in human culture is found in the Bayeux Tapestry, where Halley's comet streaks across the sky above horrified English nobles in 1066. The chroniclers illustrated armed men gesturing at the celestial visitor with looks of terror, interpreting its presence as a divine verdict against King Harold's claim to the English throne. For the Norman invaders, conversely, the same comet symbolized favorable divine intervention, a sign that God endorsed William the Conqueror's military expedition. This contrasting interpretation highlights something significant about human psychology. I tend to view cosmic events as affirmations of my pre-existing beliefs and anxieties, rather than as separate, natural occurrences. The comet itself was unaltered, adhering to the same gravitational principles that govern all celestial bodies. It was only human interpretation that converted it into either a harbinger of doom or a herald of victory. Indigenous Australian Aboriginal communities fostered rich traditions concerning cometary sightings, which differed markedly among various groups and areas. Many cultures linked these visitors with death or malevolent spirits, seeing them as rips in the fabric of the sky or as signals of imminent disaster. The Yolngu people of the Northern Territory depicted some comets as ancestral spirits journeying between sacred locations, whereas other groups saw them as warnings about breaches of traditional law or environmental disruption. These varied cultural reactions shed light on why fear-based narratives are so easily triggered when unfamiliar objects appear in my skies. Across vastly different societies and historical eras, humans have consistently seen unexpected celestial events as significant rather than arbitrary, as signs needing interpretation rather than phenomena requiring investigation. This pattern points to deep psychological origins that go well beyond rational threat evaluation. The way cometary omens circulated through ancient societies has a striking similarity to how astronomical discoveries spread through modern social media. In medieval Europe, news of celestial events traveled along trade routes and through religious channels, often arriving weeks or months after the initial sighting. By the time the information got to remote communities, it had been sifted through numerous interpretations, enhanced with local significance, and blended with existing folklore. Today's digital networks speed up this process exponentially while retaining its fundamental nature. A telescope in Chile spots an unusual object, and within hours, speculation about its nature spreads across continents faster than scientific analysis can provide clear answers. The same psychological impulses that drove medieval chroniclers to interpret comets as divine messages now appear as viral theories about alien technology or cosmic dangers. The printing press transformed how comet-related panic could spread, but it also started to introduce mechanisms for correction. Multiple sources could be compared, authorities could be challenged, and different interpretations could vie for public acceptance. The emergence of scientific bodies like the Royal Society established new frameworks for assessing celestial phenomena based on observation rather than tradition or authority. Modern institutions aim to serve similar stabilizing functions. The International Astronomical Union, NASA, and the European Space Agency act as authoritative sources for astronomical information, using standardized communication methods designed to prevent misunderstanding and panic. When these organizations declare that 3I Atlas poses no threat to Earth, they are relying on centuries of hard-won experience in differentiating between real dangers and merely unusual phenomena. Yet the fundamental human tendency to fill gaps in knowledge with dramatic stories remains as potent as ever. In the absence of complete information, and complete information about cosmic visitors takes months or years to acquire, my mind defaults to pattern-seeking behaviors that were advantageous for my ancestors in terrestrial settings but can mislead me when applied to astronomical scales. The historical record shows that comet panics adhere to predictable patterns, irrespective of the particular cultural setting. Initial sightings lead to uncertainty and speculation. Authorities try to offer reassuring explanations while admitting to the unknowns. Popular imagination then fills these unknowns with culturally significant fears: divine retribution in religious societies, foreign invasion during times of political turmoil, and technological threats in my current era of rapid scientific progress. What makes my present situation both more difficult and more promising than past eras is the democratization of information access. Anyone with an internet connection can look at the same orbital data, spectroscopic measurements, and imaging results that professional astronomers use to study 3I Atlas. The Minor Planet Center's database, NASA's Solar System Dynamics website, and observatory press releases offer an unprecedented level of transparency about the discovery and analysis process. This access opens up possibilities for genuine scientific literacy that medieval peasants or even educated nobles could never have dreamed of. Citizens can learn to distinguish between preliminary observations and peer-reviewed findings, understand the difference between scientific uncertainty and actual danger, and take part in the collective endeavor of making sense of cosmic discoveries. The enduring human pattern across all these historical examples is my tendency to turn astronomical events into stories about myself. Ancient Chinese astronomers viewed comets as reflections of imperial virtue or corruption. Medieval Europeans interpreted them through the lenses of Christian theology and feudal politics. I perceive 3I Atlas through perspectives shaped by science fiction, narratives about alien contact, and existential risks to human civilization. This pattern is not inherently problematic. Stories help me process experiences that are beyond my usual conceptual grasp. The crucial part is learning to treat these stories as provisional interpretations rather than definitive truths, and to be ready to revise them as more evidence comes in. Perhaps the most encouraging aspect of my modern approach to cosmic visitors is the speed at which international cooperation forms. Within days of the discovery of 3I Atlas, observatories around the world were sharing data, coordinating observations, and constructing comprehensive models. This response showcases my species' remarkable capacity for cooperation when faced with truly cosmic scales and timelines that make terrestrial political disputes seem insignificant. 3I Atlas is a modern trial of these ancient patterns. Will I give in to the same fear-driven narratives that turned every historical comet into a sign of disaster? Or can I create new cultural scripts that welcome cosmic visitors as opportunities for wonder, learning, and international collaboration? The answer to that question will be written not in the stars, but in my collective reaction to the stranger currently speeding through my solar system at an unparalleled velocity, carrying secrets from distant suns and challenging me to rise above the constraints of my evolved psychology. As I will find out, I am not the first civilization to face such trials, and the examples of Oumuamua and Borisov provide both cautionary tales and reasons for hope about my ability to respond wisely to cosmic mysteries. Part 8. Precedents. Oumuamua Borisov. Before 3 Atlas seized my attention with its remarkable velocity and carbon dioxide emissions, 2 earlier interstellar visitors offered vital lessons on how such objects act and how humans react to them. 1. Oumuamua, found in 2017, and 2 Borisov, discovered in 2019, set the standard for my comprehension of interstellar objects, while also highlighting the significance of thorough, patient analysis in distinguishing between genuinely anomalous phenomena and merely unfamiliar physics. Oumuamua came first, and it immediately defied expectations of what interstellar visitors ought to resemble. Initial observations showed an object with a highly elongated form about 10 times longer than it was wide and an unusual tumbling rotation that hinted at either a very irregular shape or perhaps a flat, pancake-like structure. Most perplexing was that Oumuamua displayed no visible coma or tail, even though it showed a small but definite non-gravitational acceleration as it left the inner solar system. This mix of characteristics led to intense scientific discussion and, inevitably, speculation about artificial origins. The lack of visible outgassing seemed to exclude standard cometary explanations for the acceleration, prompting some researchers to suggest that Oumuamua might be a fragment of alien technology, possibly a light sail designed to be propelled by stellar radiation pressure or debris from some incredibly ancient spacecraft. Dr. Avi Loeb, whose theory about 3I Atlas I previously examined, co-authored influential papers that put forward the light sail hypothesis as a scientifically plausible explanation for Oumuamua's characteristics. This was not baseless conjecture, but a careful analysis. If an object demonstrates acceleration without any visible loss of mass, and if that acceleration follows patterns consistent with radiation pressure, then artificial origins become a valid scientific hypothesis deserving of investigation. However, the scientific community's reaction to such extraordinary claims followed a predictable course: extraordinary skepticism. Multiple research teams worked on developing natural explanations for Oumuamua's behavior, concentrating particularly on the idea of invisible outgassing that might not be detectable by telescopic observations. The major advance came through detailed modeling of how interstellar radiation impacts the composition of small objects over millions of years. Cosmic rays and stellar ultraviolet radiation can break down water ice molecules, creating trapped hydrogen gas within the object's interior. When such an object nears a star, the warming surface can release this hydrogen in amounts too small to produce visible cometary activity, but enough to cause measurable acceleration. Recent analysis published in Nature strongly backs this hydrogen outgassing model, offering a natural explanation for all of Oumuamua's unusual traits. The elongated shape could be the result of tidal forces during close encounters with stars. The unusual rotation might reflect complex torques from asymmetrical outgassing, and the invisible acceleration aligns perfectly with hydrogen emission rates predicted by radiolysis models. 2I Borisov, discovered by amateur astronomer Gennady Borisov at his personal observatory in Crimea, presented a completely different model for interstellar behavior. From the moment it was found, Borisov showed classic cometary features: a noticeable dust coma, clear signs of outgassing, and spectroscopic signatures that identified familiar volatile compounds. As Borisov approached its perihelion in late 2019, detailed spectroscopic monitoring revealed a fascinating evolution in its composition. At great distances from the Sun, carbon monoxide and carbon dioxide were the dominant outgassing components, just as predicted by sublimation physics for objects in extremely cold environments. As solar heating increased, water vapor began to dominate the spectrum, following patterns identical to those seen in comets from our solar system. The nucleus of Borisov was found to be relatively small, likely less than 1 kilometer in diameter. Yet it generated dramatic cometary activity that made it easily visible to ground-based telescopes. The rates of mass loss measured throughout its passage through our solar system matched theoretical predictions for objects with a high volatile content, confirming that interstellar comets can hold on to significant ice reserves during their long journeys between stars. Perhaps most importantly, the behavior of Borisov showed that interstellar objects do not have to be exotic or mysterious. This visitor acted exactly like comets formed in my own solar system, implying that the fundamental physics of planet formation, the accumulation of ice and rock in cold, distant regions around young stars, operate similarly throughout the galaxy. The key lesson from comparing Oumuamua and Borisov is that interstellar objects are not a single category with predictable traits. Some, like Borisov, represent familiar physics at play in unfamiliar settings. Others, like Oumuamua, challenge my understanding and require years of careful analysis to be explained by natural processes. 3I Atlas, with its prominent carbon dioxide emissions and substantial dust coma, initially seems much more like the Borisov model than the Oumuamua puzzle. The detections of volatile outgassing by SPHEREX and the James Webb Space Telescope provide immediate evidence of active cometary processes, while Hubble's morphological observations show classic dust cocoon structures. However, the speed of 3 Atlas, which is significantly greater than that of either previous interstellar visitor, and its trajectory that takes it unusually close to planetary orbits, add elements of mystery that need careful investigation. I have learned from Oumuamua that unusual characteristics do not automatically mean artificial origins, but they do require thorough analysis before I can confidently dismiss exotic explanations. The technological progress since 2017 has greatly improved my ability to study interstellar visitors. When Oumuamua appeared, the James Webb Space Telescope had not yet been launched, and SPHEREX was still under development. Ground-based spectroscopy offered limited compositional data, and even Hubble's observations were limited by the object's small size and rapid movement. Today's array of instruments, Hubble for morphological analysis, JWST for detailed spectroscopy, SPHEREX for mapping the extended coma, and increasingly sophisticated ground-based facilities, provides an unprecedented capacity for real-time analysis of visiting objects. I can detect molecular species that would have been invisible to earlier generations of telescopes, map the spatial distribution of gas and dust with remarkable precision, and track compositional changes as objects evolve throughout their passage through the solar system. This enhanced capability makes the initial period of 3I Atlas's approach particularly thrilling from a scientific standpoint. Instead of waiting months or years for a definitive analysis, I can construct comprehensive models of composition, structure, and behavior within weeks of discovery. The importance of quick follow-up cannot be stressed enough. Interstellar visitors are temporary phenomena, usually visible for only a few months before they vanish back into the cosmic expanse. Oumuamua had already passed its perihelion by the time astronomers identified its interstellar origins, which limited the chances for detailed study. With 3I Atlas, I have the advantage of monitoring its approach, perihelion passage, and departure in real time. Future survey systems, especially the Vera C. Rubin Observatory's Legacy Survey of Space and Time, are set to revolutionize the science of interstellar objects by detecting dozens or possibly hundreds of such visitors each year. This statistical sample will allow me to understand the typical properties and behaviors of interstellar populations, making individual oddities like Oumuamua seem less mysterious and potentially artificial. The comparative timeline of all 3 interstellar visitors reveals important patterns. Discovery usually happens months before perihelion, allowing time for intensive observation campaigns. Peak activity and visibility occur around the closest approach to the Sun, when thermal heating causes maximum outgassing and dust production. Post-perihelion observations become increasingly challenging as objects move away and dim, underscoring the importance of comprehensive early study. The upcoming close encounters of 3I Atlas with Mars in October 2025 and Jupiter in March 2026 present unique opportunities that neither Oumuamua nor Borisov offered. Spacecraft already in orbit around these planets could potentially be reassigned for closer observations, providing unprecedented resolution and detail about an interstellar visitor's properties. Whether such observations will be feasible is still an open question involving complex orbital mechanics, mission constraints, and resource allocation. But the mere possibility shows how my ability to study cosmic visitors is constantly evolving, building on the lessons learned from each previous encounter. As 3 Atlas continues its approach toward perihelion, I carry with me the accumulated wisdom from Oumuamua and Borisov, patience in analysis, skepticism toward extraordinary claims, and an appreciation for the remarkable physics that governs small objects wandering between the stars. Part 9. Military and Political Implications. If it were a probe, in the improbable but scientifically plausible event that 3I Atlas is an artificial rather than a natural phenomenon, humanity would be facing its first confirmed encounter with technology of non-human origin. While current evidence strongly favors natural explanations, considering this hypothetical situation raises important questions about my readiness for truly extraordinary discoveries and the frameworks that might direct my response. The legal basis for such a situation already exists, although it was created with very different circumstances in mind. The Outer Space Treaty of 1967, approved by over 100 nations, including all major spacefaring powers, lays down fundamental principles for activities beyond Earth's atmosphere. The treaty forbids the stationing of weapons of mass destruction in space and obligates nations to prevent harmful contamination of celestial bodies. More pertinently, it assigns responsibility to the launching states for any space objects under their control. But what occurs when the space object in question comes from entirely outside my solar system? The treaty's framework presumes human actors and terrestrial politics, not cosmic visitors that predate human civilization. International legal experts have started to look into these gaps, but no binding agreements exist that address the discovery of extraterrestrial artifacts or the protocols that should guide my response. The SETI Institute and the International Academy of Astronautics have created post-detection protocols for radio signals from extraterrestrial intelligence. But these guidelines are mainly concerned with communication scenarios rather than physical objects. The protocols stress verification through independent observation, transparency in sharing data, and international coordination before any attempts at a response are made. However, these are still non-binding suggestions rather than legally enforceable international laws. NASA's Planetary Defense Coordination Office would probably be at the center of any response to confirmed extraterrestrial technology, even though its primary mission is focused on natural impact threats. The office has set procedures for trajectory assessment, risk evaluation, and public communication that could be adapted for artificial objects. The international collaboration networks established for asteroid monitoring would offer pre-existing frameworks for coordinating global response efforts. In the realpolitik of international relations, the discovery of extraterrestrial technology would undoubtedly bring up national security concerns alongside scientific ones. Major space powers might engage in passive intelligence collection, listening for radio signals, analyzing thermal signatures, or trying to detect other technological markers. However, any overt efforts to intercept or interfere with such an object would create complex legal and diplomatic problems under current space law. The suggestions by some researchers to use existing spacecraft like Juno or Mars orbiters for closer observations of 3I Atlas show how national assets could be repurposed for international scientific goals. Such missions would need careful coordination to ensure they are seen as collaborative scientific projects rather than unilateral intelligence-gathering missions. Academic works have delved into more speculative scenarios involving potential arms races or dark forest dynamics. The idea that contact with extraterrestrial intelligence might lead to existential competition instead of peaceful cooperation. However, these scenarios do not have policy consensus and are largely theoretical. Most experts in astrobiology, international relations, and space policy advise extreme caution and verification before assuming any hostile intentions. The communication strategy for handling public reaction to confirmed extraterrestrial technology would demand unprecedented coordination among scientific institutions, government agencies, and international organizations. The main objectives would be to prevent panic, preserve social order, and make sure that accurate information gets to the public before misinformation and speculation do. The swift release of raw observational data would serve several functions: enabling independent verification by scientists globally, demonstrating transparency in the discovery process, and providing a factual basis to counter conspiracy theories or sensationalized interpretations. The success of this strategy would largely depend on media literacy and the public's understanding of scientific procedures. If an extraterrestrial artifact started to transmit signals or try to communicate, the United Nations Office for Outer Space Affairs would likely organize multilateral discussions while scientific teams worked on decoding and understanding any messages. The UN framework offers established channels for international coordination, though its effectiveness would rely on the willingness of member states to prioritize collective human interests over national ones. The example of international cooperation in Antarctic research, regulated by the Antarctic Treaty System, provides a model for how humanity might handle extraterrestrial discoveries. The Antarctic Treaty designates the continent as a scientific preserve, bans military activities, and mandates international cooperation in research. Similar principles could guide the study of confirmed extraterrestrial artifacts. However, the Antarctic model is based on a fixed location that can be claimed and managed through territorial agreements. An interstellar visitor like 3I Atlas is passing through my solar system on a hyperbolic path, being accessible for only a few months before it disappears back into interstellar space. This time limitation would create immense pressure for quick decision-making and coordination. The economic consequences of discovering confirmed extraterrestrial technology could be just as significant as the political ones. Financial markets might see extreme volatility as investors try to assess the implications of contact with superior technology. Industries from aerospace to telecommunications could face sudden obsolescence or unparalleled opportunities depending on the nature and accessibility of any discovered technologies. Religious and philosophical communities would have to deal with fundamental questions about humanity's place in the universe and my relationships with other intelligent beings. The major world religions have developed various theological stances on the possibility of extraterrestrial life, but the actual confirmation of intelligent non-human technology would challenge these frameworks in ways never seen before. Educational systems would face immediate pressure to create curricula that address extraterrestrial contact, astrobiology, and the implications of cosmic citizenship. The generation of children raised in the wake of confirmed contact would live in a profoundly altered conceptual reality compared to those who came before, carrying ramifications we are only just starting to fathom. Nevertheless, every one of these hypothetical situations hinges on a vital assumption that is not backed by existing data: the idea that 3 Atlas is an artifact of technology instead of a natural occurrence. The emissions of carbon dioxide found by spherics, the structure of the dust seen by Hubble, and the spectroscopic characteristics pinpointed by JWST all indicate typical cometary behavior rather than man-made constructs. This intellectual exercise fulfills significant roles, however. By assessing our level of readiness for exceptional findings, we pinpoint shortcomings in global agreements, methods of communication, and the frameworks for making decisions that could be essential in scenarios to come. The subsequent verified interstellar traveler could very well contest our beliefs about what is considered a natural versus an artificial event. Furthermore, this activity highlights the necessity of upholding both exacting scientific standards and institutional readiness. We are obligated neither to ignore extraordinary possibilities without inquiry, nor to embrace them without extraordinary proof. The equilibrium between these two stances will shape not only how we react to 3 Atlas, but also our preparedness for the genuinely paradigm-shifting discoveries that might be waiting for us among the constellations. For the moment, 3 Atlas stands as a striking natural event, a piece of ancient ice and rock that bears the chemical imprints of a different star system, providing glimpses into the mechanisms of planet formation across the galaxy. Yet our deliberate consideration of other possibilities signifies the maturity of a species starting to earnestly consider its position in a cosmos that might conceal wonders beyond what we can currently envision. Part 10. The Coincidence Problem. Among the most captivating features of 3 Atlas's path is what certain observers have described as its strangely methodical geometry. The object moves along a retrograde orbit, proceeding counter to the direction of the planet's travel. However, its trajectory is situated only about 5 degrees from the ecliptic plane, the theoretical disk where most planetary orbits are found. This close alignment, in conjunction with meticulously timed near approaches to major planets, forms patterns that defy purely coincidental accounts and call for more profound examination. The figures narrate an extraordinary tale of celestial choreography. 3A Atlas is projected to travel within 0.19 to 0.20 astronomical units of Mars on October 3, 2025, which is approximately 28 to 30 million kilometers. This is closer than the orbit of Mars's own moon, Phobos, around the planet. Its rendezvous with Jupiter on March 16, 2026, will bring it within 0.36 astronomical units, or about 54 million kilometers, of the Solar System's most massive planet. Earth experiences the farthest encounter at roughly 1.8 astronomical units in December 2025. Yet, even this considerable buffer distance signifies a carefully determined flyby, not an arbitrary transit. Could such geometric exactness be the product of deliberate aiming by a sophisticated civilization? This inquiry merits earnest consideration, but it demands a thorough examination of what we define as coincidence within an astronomical framework and how biases in selection might shape our interpretation of importance. To assess whether the planetary encounters of 3 Atlas are true anomalies, we must first determine a baseline of expectations for random interstellar paths. Computer models can create thousands of theoretical hyperbolic orbits with differing inclinations, orientations, and speeds of entry, and then compute the percentage that experience close planetary approaches simply due to chance. The findings from such an analysis indicate that the structure of our solar system renders planetary encounters more frequent than one might intuitively believe. With their vast gravitational spheres of influence, Jupiter and Saturn can redirect or ensnare objects from substantial distances. Mars, though smaller, orbits in an area where many hyperbolic trajectories naturally meet. The statistical likelihood of an incoming interstellar object having close encounters with several planets rises to a point where it no longer necessitates unusual explanations. Additionally, we must consider the biases of observational selection, which skew our sample toward objects that possess compelling characteristics. Surveys such as 3 Atlas are designed to find objects in particular areas of the sky, especially regions close to the ecliptic plane, where the majority of solar system events take place. An interstellar visitor with an orbital inclination significantly different from the ecliptic could traverse our solar system entirely unnoticed, never being recorded in our astronomical catalogs. The recovery information that pushed 3 Atlas's observation period back to May 2025 offers critical limitations on any hypothesis of a designed trajectory. The object's path was confirmed through numerous separate observations over a period of several months, which limits the flexibility available for positing intentionally manipulated trajectories. The more information we gather, the harder it is to contend that the path was artificially devised rather than naturally shaped. The near-ecliptic inclination that at first appeared questionable seems less extraordinary when we take the galactic environment into account. Interstellar objects frequently arrive from directions associated with the galaxy's disk structure, and the ecliptic plane of our solar system is roughly aligned with this galactic disk. Objects arriving from common galactic directions will consequently have a natural tendency to cross our solar system near the ecliptic plane more frequently than from arbitrary directions. Furthermore, the optical effects of the phase angle that give 3 Atlas its seeming sunward glow can be entirely accounted for by standard dust physics without needing to propose artificial light or propulsion. The phenomenon of anti-tails happens commonly in natural comets when large dust particles, too massive for the solar wind to effectively disperse, form structures that seem to aim toward the sun when seen from particular geometric angles. However, diligent science demands that we formulate falsifiable predictions to differentiate between natural and artificial causes. If 3 Atlas were actually a probe or an artifact, we might anticipate seeing distinct signatures that natural objects are incapable of generating. These could include stable, narrowband spectral emissions, typical of man-made energy sources, structured and repeating radio signals suggesting communication or guidance systems, or non-Keplerian movement patterns indicating controlled propulsion or adjustments to its course. As of now, no observations have found any such indicators. The radio spectrum in the vicinity of 3 Atlas reveals only the background interference characteristic of space. Its movement adheres to gravitational forecasts with the accuracy anticipated from celestial mechanics. Its spectroscopic signatures correspond to those of sublimating cometary ices, not to unusual power sources or synthetic materials. The human inclination for apophenia, the act of finding meaningful patterns in random information, offers a vital psychological framework for judging apparent coincidences. Our minds evolved in settings where identifying patterns provided a survival edge, causing us to see significant connections even in truly random occurrences. When faced with uncommon cosmic events, we have a natural tendency to look for explanations involving purpose, design, or meaning, rather than accepting the influence of sheer chance. This inclination is especially strong when we are dealing with events on astronomical scales and over time frames that go beyond ordinary human experience. The notion that an interstellar object could roam the galaxy for millions of years and then, by chance, pass through our solar system during the short time that human civilization has had the means to see it can seem almost unbelievably coincidental. Yet, the immense scales in play make such seeming coincidences a statistical certainty over cosmic durations. The Monte Carlo simulations that challenge these gut feelings provide fascinating knowledge about orbital mechanics and probability. By creating thousands of random hyperbolic trajectories and computing their planetary encounter rates, we can ascertain what fraction would have close approaches similar to those of 3E Atlas. The outcomes generally indicate that such encounters happen often enough that they do not require a special cause. More advanced analysis can investigate the connections between various orbital parameters, such as whether objects with certain inclinations are more likely to have specific encounter geometries, or if particular entry speeds make visitors more prone to multiple planetary flybys. These investigations assist in separating genuinely unusual characteristics from the natural outcomes of gravitational forces in systems with multiple bodies. The forthcoming Mars encounter in October 2025 presents a prime chance to evaluate different theories about the nature of 3E Atlas. If the object were man-made, we might expect to see slight modifications in its trajectory during the Mars flyby. These could be course adjustments to optimize its later encounter with Jupiter or to alter its exit path. In contrast, natural objects should follow purely gravitational routes, dictated by their mass and velocity. High-resolution observations during the Mars encounter could also uncover structural features that are not visible from farther away. Artificial objects might show geometric precision, surface characteristics that are not in line with natural erosion, or thermal signatures that suggest internal power sources. Natural comets should exhibit irregular forms, impact craters, and heat emissions consistent with the Sun's warming of volatile-rich surfaces. The broader insight from studying the apparent coincidences of 3E Atlas is that extraordinary assertions demand extraordinary proof. But they also necessitate extraordinary caution in separating genuine anomalies from the usual results of selection biases, statistical anomalies, and human tendencies to find patterns. The cosmos is not required to operate in ways that align with our intuitive sense of probability and importance. Whether 3E Atlas is a remarkable natural event or something far more unusual, its examination showcases the significance of quantitative analysis when evaluating apparent coincidences. Only by computing real probabilities, considering selection biases, and testing specific predictions can we differentiate between significant patterns and cosmic randomness. The solution to the coincidence problem might ultimately be found not in the heavens, but in our developing sophistication as a species that can apply rigorous statistical reasoning to astronomical events that challenge our common understanding of probability, causality, and meaning. Part 11. Exotic physics or just exotic ice? As we explore more deeply the scientific enigma of 3A Atlas, we face a core question that has propelled astronomy for centuries. When faced with peculiar observations, should we propose exotic new physics or investigate if familiar physics acting in unusual circumstances can account for what we are witnessing? The record of science indicates that commonplace explanations, when thoroughly examined, frequently turn out to be more enlightening than speculative options, although at times genuinely groundbreaking discoveries do arise from apparent anomalies. The natural accounts for the behavior of 3 Atlas start with its makeup, which seems to be primarily composed of ices rich in carbon dioxide that readily sublimate as the object nears our Sun. This prevalence of carbon dioxide at great distances from the Sun aligns perfectly with theoretical forecasts for objects that originated in exceptionally cold regions and traversed interstellar space for millions of years, where only the most volatile substances would remain easily sublimable. The FEX mission's discovery of a vast carbon dioxide cloud extending for hundreds of thousands of kilometers gives direct observational proof of this sublimation process. As solar energy warms the surface of 3I Atlas, solid carbon dioxide changes directly from ice to gas, forming the expanding coma that we see. The spectroscopic validation of these carbon dioxide features by the James Webb Space Telescope provides independent confirmation for this direct physical explanation. Traces of water are less prominent in the current observations, but this pattern is completely consistent with sublimation physics. Water ice needs higher temperatures than carbon dioxide to change from a solid to a gas. Consequently, we anticipate that water vapor emissions will increase as 3 Atlas nears its late October perihelion. This offers a testable forecast. If 3A Atlas behaves according to natural cometary physics, signs of water should become more noticeable in spectroscopic data as the Sun's heat grows stronger. The captivating idea of radiolysis processed hydrogen offers another natural explanation that has similarities to the Oumuamua puzzle. Over geological periods in interstellar space, cosmic rays can break down water ice molecules, leading to trapped hydrogen gas within the object's internal structure. When solar heat warms the surface, this hydrogen can be released in amounts too small to produce visible outgassing, but enough to cause subtle dynamic changes. This radiolysis theory successfully accounted for Oumuamua's puzzling acceleration without needing to resort to artificial propulsion. Although 3 Atlas exhibits clear signs of visible outgassing that render such unseen acceleration unnecessary, the basic physics involved shows how seemingly unusual behavior can stem from well-understood processes acting over cosmic durations. The physics of dust grains presents another path for natural explanations of the unusual brightness distribution of 3 Atlas. Large dust particles close to the nucleus can generate complex optical effects when lit by solar radiation. Based on the sizes, compositions, and spatial arrangements of the particles, dust clouds can create concentrations of brightness that seem to point towards the Sun, which is the apparent forward glow that initially drew attention as possibly artificial. These anti-tail phenomena are well recorded in solar system comets, where radiation pressure and gravitational forces combine to form elaborate dust structures that can have counterintuitive appearances when observed from specific geometric viewpoints. No exotic physics or man-made illumination is needed to explain these features, only the intricate interaction of dust dynamics, radiation pressure, and orbital mechanics. The question of 3 Atlas's ultimate source introduces another layer of natural complexity to be considered. Various research groups have suggested that it originated in either the galaxy's thin disk or thick disk stellar populations, which have different ages, metallicities, and kinematic characteristics. These distinct environments would expose forming objects to different thermal histories, levels of cosmic ray exposure, and chemical processing conditions. An origin in the thin disk might point to a relatively young object formed around a star rich in metals, similar to our Sun. In contrast, an origin in the thick disk could suggest an ancient wanderer that existed before our solar system formed. The compositional clues that could help distinguish between these possibilities are still unclear, but they show how natural astrophysical processes can create objects with exotic properties using entirely conventional physics. A recent orbital analysis published in Astronomy and Astrophysics has improved the trajectory calculations for 3E Atlas, confirming its extreme hyperbolicity in barycentric coordinates, measurements taken relative to the solar system's center of mass rather than just the Sun. This analysis highlights the object's authentic interstellar origin while offering ever more precise forecasts of its future movement. The idea of unknown astrophysical processes warrants careful thought in any thorough analysis. Our knowledge of cometary physics, interstellar chemistry, and the evolution of small bodies is constantly changing as new observations challenge existing theories. 3E Atlas might show behavior that necessitates adjustments to current theory without having to propose artificial causes. However, the scientific principle of Occam's razor implies that we should fully explore natural explanations before entertaining more exotic possibilities. While unknown natural processes are conceivable, they are less radical deviations from established science than the conclusion that we are observing alien technology. The responsibility for providing proof for extraordinary assertions lies with those who make them, not with those who support conventional interpretations. This framework of burden of proof helps to create clear standards for assessing future observations of 3E Atlas. If natural cometary processes account for the object's behavior, we should continue to see spectroscopic signs consistent with sublimating volatiles, morphological features that align with dust and gas dynamics, and thermal emissions that correspond to solar heating patterns. Conversely, artificial explanations would forecast very different observational signs, such as engineered materials in spectroscopic analysis, geometric structures that are not in line with natural erosion, energy emissions that surpass contributions from solar heating, or controlled trajectory changes that defy purely gravitational motion. The peer review process will be essential in evaluating any unusual findings as they come to light. Extraordinary assertions about the nature of 3E Atlas will be subjected to intense examination by the international astronomical community, needing independent confirmation and detailed analysis before they are accepted. This procedure acts as a vital filter between initial observations and established conclusions. As 3E Atlas moves closer to perihelion, we can make specific forecasts based on natural physics that can be tested through ongoing observations. The carbon dioxide emissions should persist in patterns determined by solar heating and the thermodynamics of sublimation. Water vapor signatures should become more pronounced as surface temperatures increase. Dust production should rise as thermal stresses release more material from the surface of the nucleus. Any major departures from these forecasts would require careful examination and could potentially call natural explanations into question. Science advances through such evaluations of competing hypotheses, where observations act as the deciding factor between different theoretical models. The exotic ice hypothesis that 3E Atlas is a natural but compositionally strange object that has been processed by millions of years of interstellar travel currently offers the most thorough explanation for all the observed characteristics. This view does not require any physics beyond what we currently understand. It makes testable predictions about future observations, and it is consistent with comparative studies of other interstellar visitors. Yet science calls for intellectual humility regarding the boundaries of our current knowledge. If 3E Atlas eventually shows characteristics that defy natural explanations despite our best attempts to comprehend them through conventional physics, we must stay open to truly revolutionary discoveries. The universe has surprised us in the past with phenomena that at first seemed impossible but ultimately broadened our understanding of natural processes. Whether 3E Atlas turns out to be exotic ice or something much more peculiar, its study is a prime example of the scientific method in action: meticulous observation, rigorous analysis, and a readiness to follow the evidence wherever it may lead, all while maintaining a healthy skepticism towards conclusions that would completely change our understanding of the cosmos. Part 12. The first contact stress test. In the domain of scientific thought experiments, there are few scenarios that spark the imagination as much as the first encounter with extraterrestrial intelligence. While 3 Atlas does not exhibit any indication of artificial origin or attempts at communication, considering how humanity might react to such a find, exposes significant deficiencies in our readiness for potentially paradigm-shifting cosmic meetings. Imagine this scenario. Tomorrow morning, radio telescopes pick up a structured, clearly artificial signal coming from the location of 3 Atlas. What would follow? The initial hours would put to the test every procedure humanity has created for handling extraordinary discoveries. Following the SETI post-detection principles set by the International Academy of Astronautics, the observatory that made the detection would immediately start verification processes, confirming the signal's authenticity through several independent observations, and eliminating possibilities such as terrestrial interference, equipment failure, or natural events that might resemble artificial signals. These verification measures, however routine they may appear, would be vital in avoiding false alarms that could lead to premature public alarm or ill-advised governmental actions. The scientific community has learned valuable lessons from previous events involving pulsars, which were at first thought to be alien signals, and fast radio bursts that appeared too organized to be natural. Extraordinary assertions about extraterrestrial contact necessitate extraordinary verification before any public declaration. Concurrently, the detecting body would inform key international bodies according to preset protocols. The International Astronomical Union acts as the main coordinating authority for astronomical findings, while the United Nations Office for Outer Space Affairs offers frameworks for global cooperation on matters related to space. Both entities have contact lists and communication protocols designed for the swift distribution of vital information. The Outer Space Treaty of 1967, although drafted decades before SETI was considered a serious scientific field, lays down principles that would steer international reactions to confirmed extraterrestrial contact. The treaties focus on the peaceful utilization of outer space, the prevention of harmful contamination, and international cooperation establishes a legal basis for coordinated response measures. NASA's Planetary Defense Coordination Office, although primarily concerned with natural impact threats, would likely take on a primary role in overseeing public communications regarding any confirmed alien contact. The office has established methods for risk evaluation, trajectory analysis, and public communication that could be modified for communication scenarios. The main distinction would be in managing not a physical threat, but the psychological and societal consequences of confirmed contact with non-human intelligence. National security organizations across the globe would undoubtedly get involved in any confirmed contact situation, though finding a balance between security interests and scientific openness would be a delicate task. Intelligence agencies might try to find more signals, analyze transmission features for technological clues, or evaluate potential risks to national security. However, the international aspect of astronomical research and the worldwide ramifications of contact would likely push governments towards transparency and collaboration rather than unilateral secrecy. The current Mars orbital assets and the Jupiter mission that some scientists have suggested for observing 3 Atlas would be under immediate pressure to be repurposed if the object were to start transmitting signals. Spacecraft already in proximity to the object could potentially function as relay points, signal boosters, or platforms for close-range observation. However, the technical viability of such actions would largely depend on orbital mechanics, communication capabilities, and the particular features of any signals that were detected. The Rio scale and the San Marino scale, which were created by SETI researchers to measure the significance and consequences of potential extraterrestrial contact, would offer frameworks for evaluating the importance of any signals from 3I Atlas. These scales take into account factors like the confidence in signal verification, the information it contains, and its potential societal effects, helping officials to convey the importance of the discoveries to both scientific communities and the general public. Perhaps the most difficult aspect of a confirmed contact would be the issue of how to respond. Who, if anyone, represents humanity? Current international agreements do not have binding stipulations on this fundamental question. The SETI post-detection protocols advise against sending any response transmissions until extensive international deliberation has taken place. But these recommendations have no legal power and could be hard to uphold in reality. The democratic shortfall in cosmic communication protocols mirrors wider difficulties in global governance. While the United Nations offers platforms for international cooperation, its consensus-building methods might be too slow for situations that involve time-sensitive communication opportunities. The limited time during which 3 Atlas is within reach of our solar system would put immense pressure on making decisions quickly. Managing the media would be another major challenge, demanding an unparalleled level of coordination among scientific institutions, government bodies, and international organizations. The main objectives would be to prevent panic, combat misinformation, and make sure that accurate information gets to the public before speculation and conspiracy theories do. The success of this endeavor would largely rely on public confidence in institutions and a high level of media literacy. The prompt release of raw observational data would fulfill several vital roles in any contact situation. Open data policies would allow for independent verification by scientists around the world, show transparency in the discovery process, and offer a factual basis for public understanding. The precedent of immediate data sharing for discoveries like gravitational waves and other significant astronomical events demonstrates that this method can be effective. Economic markets would probably undergo extreme fluctuations as investors tried to gauge the effects of a confirmed extraterrestrial contact. Financial systems that are based on the assumption of terrestrial isolation could face fundamental challenges. Industries from telecommunications to aerospace could find themselves suddenly outdated or presented with unprecedented opportunities, depending on the nature and substance of any alien communications. Religious and philosophical communities would face what are perhaps the most profound consequences of a confirmed contact. Although major world religions have formulated various theological stances on extraterrestrial life, actual confirmation would test these frameworks in ways never before seen. Educational systems would be under immediate pressure to create curricula that address cosmic citizenship and humanity's role in a populated universe. The generational effect of a confirmed contact is impossible to exaggerate. Children who grow up after such a discovery would exist in a fundamentally different conceptual universe than previous generations. Their worldview would be shaped from their earliest years by the knowledge that intelligence exists beyond Earth, with consequences for everything from career paths to philosophical viewpoints that we can hardly start to envision. A technical analysis of any signals would follow well-established SETI protocols, searching for signs of information content, technological sophistication, and intentional communication as opposed to natural phenomena. The features of the signals, their frequency, modulation, information density, and temporal patterns could offer clues about the technological level and intentions of the transmitting civilization. However, it is essential to stress the crucial reality check that runs through this entire thought experiment. 3 Atlas exhibits no signs of signaling or of being artificial. Current observations show carbon dioxide emissions, a natural dust morphology, and behavioral patterns that are consistent with cometary physics. This scenario is an exercise in preparedness rather than a prediction based on actual evidence. The benefit of such exercises is in pinpointing deficiencies in our institutional structures, communication methods, and international cooperation mechanisms. By considering these scenarios before they happen, we can create better protocols for handling truly extraordinary discoveries when they do occur. Furthermore, this exercise underscores the importance of upholding both scientific rigor and institutional readiness. We must not dismiss extraordinary possibilities without proper investigation, nor should we accept them without extraordinary proof. The balance between these two positions will shape not only our reaction to potential signals from 3E Atlas, but also our preparedness for the genuinely transformative discoveries that may be waiting for us among the stars. The stress test shows that while humanity has many of the institutional components needed to manage extraterrestrial contact, there are still significant gaps in international coordination, democratic involvement, and public communication. These deficiencies reflect broader challenges in global governance that go far beyond SETI scenarios. Perhaps most importantly, this thought experiment illustrates why the scientific community's measured, evidence-based approach to studying 3E Atlas serves humanity's long-term interests by setting clear standards for evaluating extraordinary claims, maintaining transparency in research, and fostering international cooperation around shared scientific objectives. We are building the foundations for a wise response to whatever discoveries the universe may hold. Whether 3E Atlas ultimately turns out to be a remarkable natural phenomenon or exhibits unexpected characteristics, our careful preparation for extraordinary possibilities reflects the growing maturity of a species that is beginning to take seriously its responsibilities as cosmic citizens in a universe that may hold surprises beyond our current imagination. Part 13. The Great Filter Question. The chance, no matter how slim, that interstellar objects like 3E Atlas could be artifacts from alien civilizations compels us to address one of the most significant questions in astrobiology. If we ever do find proof of extraterrestrial technology, what would that reveal about the destiny of intelligence in the cosmos? The answer to this inquiry touches upon one of the most sobering ideas in modern science, the Great Filter hypothesis, and could fundamentally alter our perception of humanity's cosmic future. The Great Filter is a theoretical explanation for the Fermi paradox, the seeming inconsistency between the high likelihood of extraterrestrial civilizations and the complete absence of any evidence for them. According to this hypothesis, there is some exceptionally challenging evolutionary stage that stops most life from achieving technological maturity. The filter might be in our past, in which case we are incredibly lucky to have navigated through it. Or it could be in our future, implying that technological civilizations usually annihilate themselves before they can expand across the galaxy. If interstellar probes like 3E Atlas were indeed the remnants of extinct civilizations, they would offer sobering proof that the Great Filter is ahead of us, not behind us. It might be that advanced species frequently develop the technology necessary to explore other star systems, only to fall prey to technological self-destruction, environmental collapse, or other existential threats before they can establish a lasting galactic presence. Dr. Avi Loeb and other scientists have contended that finding alien artifacts would completely reset humanity's priorities concerning space exploration, the mitigation of existential risks, and long-term survival plans. If other civilizations have emerged and disappeared throughout the galaxy's history, leaving behind only scattered technological remnants as proof of their existence, it would indicate that technological intelligence encounters systematic obstacles that we have not yet grasped or surmounted. However, detractors point out that this interpretation means accepting extraordinary assertions without extraordinary proof. The lack of confirmed alien artifacts signifies that we are still in the domain of speculation, not established reality. Natural explanations for interstellar objects such as 3E Atlas, Oumuamua, and Borisov are more in line with current observations than theories involving alien technology. The natural view of these visitors already gives us profound insights into cosmic processes and the formation of planets across the galaxy. The familiar chemistry of Borisov showed that the fundamental physics of planet formation, the buildup of ice and rock around young stars, works in a similar way in different star systems. The carbon dioxide-rich composition of 3E Atlas adds to this understanding, demonstrating how various stellar environments can create objects with different levels of volatile content. This expanding collection of interstellar visitors provides a unique look into planetary science beyond our own solar system. Each object has chemical signatures that indicate the conditions around the star where it was born, isotopic ratios that help determine formation timelines, and structural features that shed light on billions of years of thermal and dynamic evolution. These insights improve our understanding of galactic ecology without needing to resort to exotic explanations. Nevertheless, the possibility of technological artifacts among interstellar populations brings up important questions about detection techniques and statistical analysis. A galaxy filled with natural interstellar debris could effectively hide artificial objects, making them hard to spot with standard astronomical observations. This possibility highlights the need to develop instrumental signatures that could differentiate between manufactured materials and natural compositions. The quest for such signatures is similar to the efforts in SETI research to find artificial signals amidst the background of natural cosmic radio noise. Just as radio astronomy has created advanced methods for identifying structured transmissions, optical and infrared astronomy might have to devise new techniques for spotting technological materials, geometric regularity, or energy sources that are not consistent with natural processes. The philosophical consequences go beyond the issue of detection to fundamental questions about intelligence and cosmic evolution. If technological civilizations regularly appear throughout the galaxy only to encounter systematic existential threats, it would imply that intelligence itself might be a maladaptive evolutionary trait on cosmic timescales. The same cognitive skills that allow for tool use, scientific discovery, and space exploration might also make species prone to self-destructive behaviors. On the other hand, finding proof of successful, long-lasting civilizations would offer encouraging evidence that technological species can overcome existential risks and establish a sustainable presence in the galaxy. Such findings might provide insights into effective survival strategies, paths of technological development, or social structures that encourage long-term stability. The timescales involved in these scenarios are far greater than human historical experience. The rotation periods of galaxies last for hundreds of millions of years. The lifetimes of stars stretch over billions of years. And the universe itself has been in existence for almost 14 billion years. Any technological artifacts we might find could be from civilizations that emerged and disappeared long before complex life forms developed in Earth's biosphere. This temporal view underscores both the rarity and the importance of the present moment in cosmic history. Humanity has only been around for a fraction of the universe's existence, yet we have already created the technology needed to detect and study interstellar visitors. Whether we are a typical or an unusual evolutionary outcome is one of the great unknowns in astrobiology. The rapidly advancing capabilities of astronomical surveys are set to revolutionize our understanding of interstellar object populations within the next 10 years. The Vera C. Rubin Observatory's Legacy Survey of Space and Time is expected to detect hundreds or even thousands of interstellar visitors each year, providing statistical samples large enough to identify systematic patterns and anomalies. This statistical method offers the best prospect for resolving questions about the prevalence of natural versus artificial objects among interstellar populations. Rare technological artifacts might become identifiable through systematic deviations from the distributions expected for natural populations. Alternatively, comprehensive studies might definitively establish that all interstellar objects follow natural formation and evolution processes. Even if the results are negative, finding no proof of alien technology among large samples of interstellar objects. This would still provide valuable information for astrobiology and SETI research. Such findings would help to constrain models of the prevalence of technological civilizations, suggest that artifact-producing species are less common than optimistic predictions suggest, or indicate that advanced civilizations use technologies that are currently undetectable by our methods. The existential significance of these questions goes far beyond academic interest. If humanity is a typical technological species, our destiny might be similar to that of countless other civilizations throughout galactic history. Understanding the challenges that other species have faced and potentially overcome could inform our own strategies for long-term survival and cosmic expansion. The concept of cosmic loneliness versus a cosmic community has a profound effect on human perspectives on meaning, purpose, and responsibility. A universe inhabited by technological species would present opportunities for communication, collaboration, and the shared exploration of cosmic mysteries. A universe where technological intelligence regularly emerges only to self-destruct would suggest that consciousness itself faces systematic existential challenges. For now, objects like 3 Atlas continue to offer insights into natural cosmic processes while challenging our assumptions about what is typical versus anomalous behavior in interstellar populations. Whether future discoveries reveal evidence of alien technology or confirm that we are studying natural phenomena, the investigation itself is an example of humanity's growing capacity for rigorous scientific inquiry into questions that touch the deepest levels of cosmic significance. The great filter question ultimately remains unresolved, awaiting evidence that may come from the careful study of interstellar visitors, radio searches for technological signatures, or the direct exploration of nearby star systems. Until then, we continue to examine each cosmic messenger with the scientific rigor and philosophical humility appropriate for a species seeking to understand its place in a universe that may hold surprises beyond our current imagination. Part 14. Wonder over Fear. As we approach the conclusion of our exploration into the scientific puzzle of 3 Atlas, it is time to take a step back and review the evidence with the clarity that a comprehensive analysis provides. When we gather the observations from Hubble's morphological studies, JWST's spectroscopic inquiries, and SphereX's compositional mapping, a coherent image takes shape. We are examining a remarkable natural comet that carries volatile-rich ice and dust from another star system. The detection of carbon dioxide and water vapor offers unequivocal proof of active sublimation processes that do not require any unusual explanations. The teardrop-shaped dust coma, as seen in Hubble's images, corresponds to theoretical models of cometary activity with extraordinary accuracy. The constraints on the nucleus size, estimated to be between 0.32 and 5.6 kilometers in diameter, are perfectly in line with what is expected for objects that could retain volatile ices during millions of years of interstellar travel. This convergence of independent observations showcases science at its most effective. Multiple instruments, operated by different teams using various methods, all arriving at compatible conclusions about the fundamental nature of 3 Atlas. No single observation on its own would be conclusive, but the collective weight of the evidence presents a strong case for natural rather than artificial origins. The disparity between journalism's demand for novelty and science's dedication to accuracy explains why initial speculations about alien technology became so prominent in early reports. News cycles require fresh perspectives and compelling stories, often highlighting the most exotic possible explanations before peer review and archival recovery data can offer more mundane conclusions. This friction between media timelines and scientific timelines highlights a fundamental difficulty in communicating about cosmic discoveries. The most reliable information emerges gradually through careful analysis, cross-validation, and peer review. While public interest is at its peak immediately after initial discovery announcements, by the time definitive conclusions are reached, attention has often moved on to new mysteries. The international cooperation that has defined the research on 3 Atlas shows humanity's remarkable ability to work together when faced with genuine cosmic puzzles. The Minor Planet Center coordinated global observations within hours of the discovery. NASA and ESA shared telescope time and data without any institutional obstacles. University teams from around the world provided specialized knowledge in orbital dynamics, spectroscopy, and compositional analysis. This spirit of collaboration goes beyond the political divides that often characterize terrestrial matters, suggesting that cosmic encounters could act as catalysts for broader international cooperation. When confronted with phenomena that are far beyond human timescales and that challenge terrestrial viewpoints, our species shows an inspiring capacity for collective scientific effort. The educational significance of the study of 3A Atlas goes well beyond astronomical knowledge. The object's carbon dioxide-rich composition informs us about the survival of volatiles in interstellar environments, the processes of planet formation around other stars, and the chemical diversity that is present throughout our galactic neighborhood. These insights enhance our understanding of cosmic chemistry while offering tangible links between abstract astrophysical theories and observable phenomena. The advanced set of tools that has allowed for the real-time analysis of 3I Atlas is the result of decades of investment in space-based astronomy. Hubble's optical imaging capabilities, refined over 30 years of orbital operations, provide morphological insights that are unattainable from ground-based telescopes. JWST's infrared spectroscopy, which represents the latest in detector technology and precision pointing systems, identifies molecular species with unparalleled sensitivity. Spherex's wide-field mapping capabilities uncover extended structures that single-pointing observations might overlook entirely. This instrumental ecosystem is a prime example of how long-term scientific investments yield benefits in unforeseen ways. Telescopes that were designed to study distant galaxies and exoplanet atmospheres can be seamlessly adapted to analyze interstellar visitors, demonstrating the interconnected nature of astronomical research and the importance of having diverse observational capabilities for amateur astronomers and citizen scientists. 3 Atlas provides observing opportunities that link backyard telescopes with cutting-edge research. Although the object is too dim for easy detection without specialized gear, experienced observers with larger telescopes and sensitive cameras may be able to capture images during favorable viewing periods. These observations add to the global monitoring effort while creating personal connections to authentic cosmic exploration. The mission concepts that have been proposed for a closer examination of 3 Atlas, such as potential observations by Juno during the Jupiter encounter or by Mars orbiters during the October flyby, show how existing space assets can be repurposed for new scientific goals. These proposals highlight the adaptability of modern spacecraft operations while underscoring the importance of having rapid response capabilities to study transient events. However, the true importance of these mission concepts is not in their technical viability, but in their demonstration of humanity's increasing sophistication in cosmic exploration. We now regularly operate spacecraft throughout the solar system, maintain communication networks over interplanetary distances, and coordinate complex observation campaigns that involve multiple space and ground-based assets. The cultural shift that is represented by our response to 3 Atlas should be recognized alongside the scientific accomplishments. Instead of viewing this cosmic visitor as a sign of impending doom or a divine message, we have treated it as a chance for learning and discovery. This change from fear-based to curiosity-based reactions to celestial events signifies genuine progress in human intellectual development. The transparency of the process that has marked the research on 3 Atlas, with observations, data, and analysis being freely shared through international databases, shows how open science speeds up understanding while fostering public trust. Citizens can access the same orbital data, spectroscopic measurements, and imaging results that professional astronomers use in their research, taking part directly in the process of cosmic discovery. This democratization of astronomical data opens up educational opportunities that previous generations could only have dreamed of. Students can download real observational data, conduct their own analyses, and draw their own independent conclusions about cosmic phenomena. The divide between professional research and public involvement continues to narrow as data access becomes easier and analysis tools become more widely available. Looking ahead, 3 Atlas serves as a model for how humanity might handle future interstellar visitors. The rapid response protocols created for this object, the mechanisms for international coordination, and the multi-instrument observation strategies will be the templates for studying cosmic messengers in the future. Each encounter teaches us not only about specific objects, but also about how to carry out effective astronomical research in an age of ever-increasing discovery rates. The upcoming observation periods, the October perihelion passage of 3 Atlas and its closest approach to Earth in December, provide final chances to test our understanding against direct measurements. If the natural comet hypothesis is correct, we should see an increase in water vapor emissions, greater dust production, and morphological changes that are consistent with intensifying solar heating. These predictions offer clear standards for confirming our current understanding. Whether these predictions are borne out or reveal unexpected surprises, the investigation of 3 Atlas is a prime example of the scientific method applied to cosmic puzzles. Careful observation, hypothesis testing, international cooperation, and a readiness to be surprised by what the universe reveals. This approach serves humanity's long-term interests better than either the premature acceptance of extraordinary claims or the reflexive dismissal of unusual observations. The legacy of 3 Atlas will ultimately be defined not by whether it turns out to be exotic or ordinary, but by how well its study advances our understanding of interstellar objects, improves our capabilities for cosmic exploration, and demonstrates our growing maturity as a species capable of rigorous scientific inquiry into the most profound questions about our place in the universe. As this remarkable visitor continues its journey towards the outer solar system, it takes with it our aspirations for continued cosmic discovery, our admiration for the elegant physics that governs celestial mechanics, and our growing confidence in humanity's ability to respond to cosmic mysteries with wisdom instead of fear. Part 15. Our Place in the Cosmos. Ultimately, 3 Atlas compels us to face a profound reality about our cosmic predicament. We are a nascent species, just a few 100,000 years old, observing fragments of ancient starlight and primordial ice as they drift by our small haven in an immense ocean of space and time that covers billions of years and trillions of kilometers. This viewpoint, however humbling it may be, stands as one of humanity's most significant intellectual accomplishments, the capacity to comprehend our position in a universe far more vast than our ancestors ever conceived. Even if 3 Atlas is shown to be just a natural comet, the use of quotation marks around that phrase exposes the inadequacy of such a notion. There is nothing just about material that originated around another star, endured millions of years of wandering through the interstellar expanse, and now presents itself to our telescopes with chemical signatures that tell of processes that took place billions of years ago in stellar environments we may never reach. The carbon dioxide and water vapor that we detect now started their cosmic voyage when the universe itself was younger, when different stars lit up the galaxy, and when Earth's biosphere was profoundly different from the world we live in today. This temporal perspective completely changes our understanding of what is considered extraordinary versus ordinary. By cosmic measures, the rise of a technological civilization on Earth is an event far more remarkable than the passage of interstellar debris through our solar system. Intelligence capable of constructing telescopes, sending spacecraft, and decoding the chemical makeup of objects from other star systems has appeared only very recently in cosmic history, and perhaps only very rarely throughout the galaxy. If future observations were to somehow show that 3 Atlas is technology rather than natural ice, a possibility that current evidence does not support, but which scientific integrity demands we acknowledge, humanity would experience the most profound paradigm shift in our species' intellectual history. We would have to reconsider our cosmic context, our long-term survival strategies, and our duties as inhabitants of a universe populated by intelligence. Such a finding would immediately put into effect the international treaties, coordination protocols, and communication frameworks that we discussed earlier in our investigation. More significantly, it would be a test of our wisdom, our capacity for cooperation, and our ability to react to cosmic-scale challenges with the necessary gravity and care. But the reality check that runs through all such speculation remains clear. Earth will not get any closer than approximately 1.8 astronomical units to 3 Atlas in December 2025. At its nearest point, this visitor will be about 270 million kilometers away, roughly the distance between Earth and Mars at their closest approach. We are in no physical danger from this object, irrespective of its ultimate nature or composition. This assurance of safety allows us to study 3 Atlas with pure scientific curiosity rather than existential dread. We can examine this visitor as we would any other cosmic event, aiming to understand its characteristics, origins, and behavior without the sense of urgency that might impair our judgment if it were to present an actual threat to our planet or civilization. This privilege of dispassionate analysis is a victory for human intellectual progress. Our ancestors viewed comets as omens of disaster precisely because they did not have the scientific frameworks needed to distinguish between real risks and imagined threats. Today, we have those frameworks, along with the technological means to track, study, and understand cosmic visitors with unprecedented accuracy. The humility that comes from a cosmic perspective serves important roles beyond mere intellectual integrity. The acknowledgement that our understanding is still incomplete, that surprises are waiting for us among the stars, and that the universe follows physical laws rather than human desires, helps to adjust our expectations and reactions to cosmic discoveries. Our experience with past interstellar visitors, the mysterious Oumuamua with its unusual acceleration and the well-behaved Borisov with its classic cometary features, shows that interstellar objects do not fit a single mold or follow predictable patterns. Each visitor has its own tale to tell about stellar environments, planetary formation processes, and the complex physics that governs the evolution of small bodies over galactic timescales. 3 Atlas contributes another chapter to this expanding collection of interstellar stories. Its carbon dioxide-rich composition, high velocity, and meticulously coordinated planetary encounters offer new data points for understanding how objects are formed around other stars, survive their interstellar journeys, and interact with the star systems they meet during their cosmic travels. The instrumental progress that has enabled the real-time analysis of 3 Atlas, from Hubble's morphological imaging to JWST's molecular spectroscopy and SpherX's extended coma mapping, provides models for studying future interstellar visitors. The next object found by the Vera C. Rubin Observatory's Legacy Survey of Space and Time will benefit from the techniques, protocols, and international coordination mechanisms that were developed through our investigation of 3 Atlas. This technological and methodological advancement is a testament to humanity's growing sophistication in cosmic exploration. We are no longer just passive observers of celestial events. We actively investigate them using instruments that can measure chemical compositions across interstellar distances, track trajectories with extraordinary precision, and coordinate global research campaigns within hours of a discovery. The civic lessons that are part of the 3 Atlas research go far beyond astronomical education. The ability to separate established facts from initial speculation, to handle uncertainty without giving in to anxiety, and to assess extraordinary claims against appropriate standards of evidence are valuable skills for citizens in many situations beyond cosmic mysteries. The media literacy skills needed to navigate the coverage of astronomical discoveries, recognizing the difference between peer-reviewed analysis and sensational speculation, understanding how scientific confidence changes over time, and appreciating the distinction between uncertainty and danger are directly transferable to other areas where scientific information meets public policy and personal decision-making. Perhaps most importantly, 3 Atlas challenges us to broaden our temporal and spatial viewpoints beyond the limited scope of human experience. The object we are studying has journeyed farther than human civilization has existed, carrying materials that are older than complex life on Earth and following gravitational laws that operate with mathematical precision across cosmic scales that are far greater than terrestrial geography. This expansion of perspective acts as a remedy to the narrow-mindedness that often defines human affairs. Political conflicts that appear immense from a terrestrial standpoint seem much smaller when seen against cosmic timescales. International borders that separate our species become invisible when viewed from the perspective of an object that has roamed between star systems for millions of years. The call to wonder that 3 Atlas represents goes beyond scientific curiosity to include our collective response to the magnificent complexity of the universe we are part of. The carbon dioxide-rich coma that surrounds a kilometer-scale nucleus is a demonstration of simple physics in action, the direct change of solid ice to gas as stellar radiation warms ancient volatile materials. Yet, this simple physics has profound implications for understanding planet formation throughout the galaxy, chemical processing in interstellar environments, and the cosmic ecology that links star systems across vast distances and timescales. The ordinary processes of sublimation and dust dynamics, when applied to an extraordinary visitor from interstellar space, provide insights into cosmic processes that cover galactic scales. The image that will stay with us as 3 Atlas finishes its passage through the solar system, a wisp of carbon dioxide-illuminated dust around a tiny nucleus carrying chemical signatures from another star, captures both the simplicity and the profundity of cosmic processes. This visitor is neither an omen nor an artifact, but something perhaps even more remarkable: direct physical evidence of the chemical and dynamical processes that shape our galaxy. Our response to this cosmic messenger will be remembered not for the fears it did not justify or the exotic explanations it did not support, but for the scientific collaboration it sparked. The international cooperation it showed, and the expansion of perspective it offered to anyone willing to consider their place in a universe far grander and more wonderful than our terrestrial experience might suggest. Fear contracts our world, turning cosmic mysteries into threats and closing our minds to possibilities that are beyond our current understanding. Wonder expands our world, opening our minds to the magnificent complexity of a universe that continues to surprise, educate, and inspire those who are brave enough to look up at the night sky and ask what secrets might be concealed among the stars. 3A Atlas, speeding through our solar system at 200,000 kilometers per hour while bringing news from distant suns, invites us to choose wonder over fear, curiosity over anxiety, and a cosmic perspective over terrestrial narrow-mindedness. Whether we accept that invitation will determine not just our understanding of this particular visitor, but our readiness for the cosmic discoveries that await us in the decades and centuries to come.